I want you to see this molecule here. That is the alkyl halide, right? You can do substitution reactions. You can do elimination reaction with it. It is bromine sitting on the secondary carbon. So that is kind of what you can see here right now. So using just that substrate only, don't look at that right now, just that only. Can you figure out what mechanism will take place? The answer is you cannot, because the most of the reaction E1, E2, SN1, SN2, those are the two-body issue, right? So you cannot just tell by looking at this what reaction will take place. You have to look at what you're going to react with. So we have two different reagents given the same molecule. And then one is this is a conjugate base form of the T-butanol, right? The K is a potassium salt. The oxygen is a negatively charged. This is a negatively charged oxygen there. That's a neutral alcohol, right? So those two reagents are clearly different. That is a strong reagent. That is a very weak, right? You can probably get some mechanism based on these two right now because this is the T-butoxide. I mean, most of the strong base can be a strong glucopile. But in the case of the T-butoxide, do you think that will become a good glucopile because of the oxygen having a high electron density? So this is a kind of exception we talked about. Most of the cases, strong base becomes a strong glucopile, except it becomes aesthetically hindered. The bulky base doesn't become a good glucopile. And then T-butoxide is one of the examples. So this already limiting down that we're not going to see the substitution reaction because these reagents are too it's a strong but not a good glucopile because of the aesthetic hindrance. So what this can do is elimination, right? That's basically what we can say. Now, coming back to this one, we even cannot say anything from these structures. There's something that you probably could pay attention here. Even though you use the strong glucopile, substitution reaction with this will be challenging. Why did I say that? Is there any hint that you can recognize for that statement? I mean, that's a secondary bromide, right? The secondary halogens are kind of in gray areas. You know, you've probably seen the reactivity SN2 reactions need aesthetically less in the substrate, meaning that primary halide is the best, then secondary, and then tertiary. In the case of the elimination reactions, I'm talking about E2 elimination reactions, tertiary is the best, secondary and can happen, but primary is bad. So when it becomes a tertiary, when it becomes a primary, you know, it has certain choices. But secondary is kind of it can go along with anything depending on what you have. Secondary can have a substitution reactions, but what I don't think this would be good for the substitution reaction is an adjacent carbon. There's a quaternary carbon right there. You remember that if you got the quaternary carbon next to the whatever that together, even the primary, that positions is giving too much hindrance for the substitution reaction at that point. So because of that, even with a strong glucopile, I don't think substitution reaction will happen. But that is not a glucopile either. So in both cases, it's basically elimination reactions are only choices for the molecule. And this is a strong base, and that is a solvent. Shouldn't be strong as a weak base with glucopile. So let's talk about what's going to happen with these two. Strong reagents like that T-butoxide will make an elimination reaction, make a double bond. But you know that elimination reactions, the position of double bond changes depending on which proton base will pick it out. If the base pick up proton from this side, make a double bonds, you get this. If the base can pick up this proton, then you get a double bonds there. Which one do you think will be formed? And then something that you probably need to remember that the more substituted double bonds becomes the more stable, right? So the more substitutions on double bonds becomes a major product. Between these two, the double bonds, just having a one carbon substitution, another carbon substitute to the double bonds. But these double bonds, you can say, is a di-substitute double bond, two carbon substituents. That double bonds, 1, 2, 3, is a three carbon substituents to the double bonds. So if I ask you which of these two would be more stable, then you should pick this one. And that should be the major, right? So this is a thing that I'm telling you, you cannot just memorize the pattern of the answer in question. That is not going to happen. This is not going to happen at all. Why? I mean, that looks like a more stable than that one, so that should be formed. Double bond should be made. Double bond can be made from these two, double bond can be made those two, so we should have that, right? Why is that happening? No, there's no hydrogen. But yeah, I mean, of course, this question, you probably can use that, but that's not the only reason. The reason why this was not happening because you see this carbon, there's no hydrogen. If there's no hydrogen, you cannot take the hydrogens out and make a double bonds. If you make a double bonds here, this one method was a mistake. So basically, this is a pretty wrong answer. You may get that by just, punch or just memorizing how to solve the question, do not pay attention to actual structures, then you probably just write it out. And then, this is something that you should do. You should work it out. So that is not possible because there's no hydrogen there. So only thing the base can come and pick it up is that hydrogen here on the transposition to the bromine, because we talked about anti-covalent conformation is equal to trans-diaxial the cyclohexane conformations. It must be trans relationships. So these hydrogen opposite side of the bromine, so that can be picked out by the base, strong base, directly making a double bonds. So that's the only product it can give as an E2 elimination reaction. But temperature changes these days. If you're using this one, that can also make the elimination reactions, right? And should we expect the same product? It's the same elimination reaction, right? Even though this is an E2 elimination reaction, E1 could make the same product. So that's something that I'm telling you. Depending on what happens, your product changes. You just cannot memorize this thing. I mean, from the beginning, my message to you is the same. You really need to work it out. Small changes in the reagent can change the fate of the molecule completely in different forms.
Okay, and that hydrogen, the trans hydrogen to the bromine is being taken because it's the anti-covalent, which is like easier for that molecule.
It's not easy. That's the only way to make an E2 elimination happen.
Oh,
yeah.
So it won't happen like the same covalent.
The same covalent.
Okay.
Anti-covalent, which is the equivalent to the trans-diaxial, the cyclohexane. So that's the only reason why. I mean, that's the reason why only this molecule formed as a product. I mean, we'll come back to that concept one more time with the other example to clarify. But this one is because there's no hydrogen there. This only hydrogen on that side. Okay. Question? So that's the kind of I can tell you. You cannot simply just make a more substitute double bond no matter what. There's gotta be hydrogen there to be hydrogen. Anyway, E1 elimination. This is the basically weak base, right? The neutral alcohol, not a strong reagent. So no E2 can happen, no SL2 can happen. I mean, that's very key alcohol, so I don't think that's the two question. But E1 and SN1 is what can happen with that. The first thing of the E1 and SN1 is the formation of the carbocation. So this bromine gonna come off with electrons. That's gonna creating a carbon cation right there, right? Then what I'm telling you, you gotta remember, as soon as you see the carbon cation, it's a possibility to be rearranged. Will this be arranged? If that's a secondary carbon cation, this hydrogen moving over there gonna make the secondary carbon cation. Probably that's not gonna happen. But right next position, we got the methyl groups there. If you move one of the methyl groups over here, then you can make a tertiary carbon cation. That energy could be better than secondary carbon cation, so rearrangement would happen. This is the rearranged, more stable carbon cation. Now, things can happen with that. You expect E1 elimination with it. You expect SN1 products with it. So just telling you, I mean, this is the problem that can happen because if you move that hydrogen up, you get the secondary carbon cation, which is the same as the other one, which there's no advantage of doing that. And then from the E1 elimination, from the most stable carbon cation, you can lose the hydrogen from that hydrogen, make a double bonds here, right? That is this product. If you move the hydrogen from that methyl groups, you're gonna make a double bonds over here. If you make the hydrogen comes out from that carbon, then you're gonna make that one. So it's a multiple double bonds forms. Among these three, you can imagine one of the major products, right? So then what do you remember? The stability of the double bonds. Which ones are more stable? All carbon substitute with double bonds are more stable, right? So this one has a 1, 2, 3 carbon substituents. It's a tri-substitute double bonds. That one is just a 2. That one has a 4. So you can imagine which one will be 3. So these will be the major. Well, you should also probably expect the SN1 products. That means these things capture them in substitution products. That will also happen as well. And then you could probably should think about that should also make an elimination as well and the substitution too. So if you have that proton pick up by the base, or base come, which is a big base, come and pick up this proton, then you're going to make a double bonds right there. That is going to be another potentially there in the final solutions. But this is a major intermediate, and that we're expecting these will be the major products, that will be the minor.